In a previous discussion, we discovered that the length of u squared times the length of v squared is always the same thing as the square of u dot v plus the square of the length of the cross product of the two vectors. In a previous discussion, we also discovered that u dot v is the length of the first vector times the length of the second times the cosine of the angle between them, where we take the angle between the two vectors to be between 0 and pi radians. It's worth mentioning that the sine of such an angle is not negative. If I combine those two facts, I find out that this must always be true. In what follows, I'm just going to do some algebra and rearranging, so I'll do this without comment. Lengths of vectors are not negative, so when I do, for instance, the square root of the length of u squared, I'll certainly just get back the length of u. Likewise for this factor, likewise for that factor. But when I take the square root of the square of a number, generally speaking, I should write down the absolute value of that number. So really, when I do the square root, I should write absolute value sine of theta, but for theta between 0 and pi, sine of theta is not negative, so the absolute value is not necessary. Rearranging, I find out that the magnitude of u cross v is the product of the magnitudes of the two vectors times the sine of the angle between them. Two comments. Firstly, this is very reminiscent of what went on with the dot product. Secondly, this gives me a better picture in my mind of what this cross product looks like. U cross v is a vector that sticks up out of the plane containing u and v, and the length of it is this expression. We're going to solve a simple geometry problem in a moment, taking advantage of this fact. The first question I want to look at is this. Imagine that you have two vectors. We arrange their initial points to be at the same place. We form the parallelogram that we would use if we wanted to calculate u plus v and u minus v, and so on. I'd like to know what the area of that parallelogram is. For convenience, in the picture that I'm about to draw, I'm going to draw the vector u as though it were horizontal. That doesn't alter anything significant. This corresponds to just turning the piece of paper until the u is horizontal, or equivalently, changing the position of the camera until the u is horizontal. The area of a parallelogram is the length of its base times the perpendicular height. Having changed my point of view to this, the length of the base is just the magnitude of vector u. Vector v is most likely tilted in some way with respect to vector u. The perpendicular height is this distance. If we can figure out what the perpendicular height is, I'll just multiply that number by the length of u, and we'll have the area of the parallelogram. Positioning ourselves at the end point of vector v and traveling straight down to u in a right angle manner, I can extract a right triangle out of the situation. Writing down the formula for sine of theta, which is opposite over hypotenuse, rearrange it a little bit, and you find out that the perpendicular height is actually the length of vector v times sine theta. This tells me that the area of the parallelogram that I'm interested in is the length of the first vector times the length of the second times the sine of the angle between them. But one of the results that we got was the length of u times length of v times sine of theta is the magnitude of u cross v. So the area, which is equal to that, which is that, which is equal to that, must be the magnitude of u cross v. If I have a parallelogram made by connecting two vectors u and v and forming the usual parallelogram, the area of that one is the magnitude of u cross v. If we know the components of u and v, we can easily calculate such a thing. Leaving the routine details out, the cross product works out to be 2i minus j minus k. It is the magnitude of that vector that gives me the area of this parallelogram. The indicated parallelogram has area square root of 6 square units. The last topic that I want to talk about in this video is this. Suppose I have a parallelogram. What I'm going to do is I'm going to move this parallelogram in three-dimensional space. I might move it up or down, I might move it this way, and I might push it back into the plane of the paper or pull it out, or I could do all of those things. Having done so, I can think about connecting corresponding corners with straight line segments. The resulting shape is reminiscent of a rectangular box, but instead of the faces being parallel rectangles, they're parallel parallelograms instead. This is called a parallelepiped. If I could tell you how to generate the base of the thing and what you have to do in order to manufacture this clone of the base, you would know everything about the parallelepiped and therefore, in principle, should be able to calculate any quantity of interest related to it, like its surface area, or in our case, the volume. I'm going to think of the first arrow that we drew, the bottom edge, as being vector u. To make the base of the parallelepiped, I need to name something else, so I'll call this vector v, and then the vector that connects the corner that u and v come out from, or emanate from, that leads me up to my clone of the base, I'll call w. It's important to understand that the names mean absolutely nothing. They're just bookmarks for these different arrows. I could have called that one W, that one U, and that one V, or any one of 6 different possibilities. The volume, just like before, is the area of the base times the perpendicular height. The base is a parallelogram formed by vectors u and v, and we just saw a moment ago how to calculate the area of such a thing. If we can figure out what the perpendicular height is, we'll be ready to calculate things. It's worth remembering that the cross product of u and v is at right angles to both u and v, u cross v is at right angles to the plane formed by the base, and since the top is parallel to that plane, u cross v is also at right angles to this plane. I'm going to draw another picture. I'm going to turn my picture so that the plane containing u and v is going to be viewed edge on, sort of a sideways perspective. Vector W connects the two planes. A perpendicular normal vector, I could use u cross v, or u cross v might look like that, but in either case, it's at right angles to both of the planes. Keeping in mind that I have two different possible orientations, if I take vector W and project it onto the right angle direction, the projection is either a positive multiple of u cross v or a negative multiple of u cross v. We'll eliminate the ambiguity in a moment. I want to find the projection of vector W onto the direction of vector u cross v. We figured out how to do this some time ago. We form the dot product of the vector that we are projecting, the W, with the vector whose direction we're projecting it onto, u cross v in this case. We divide by the square of the magnitude of the vector upon whose direction we're projecting W. And then this is a number. This is multiplied by the vector that we're projecting onto. The magnitude of a number times a vector is the absolute value of the number times the length of the vector. This u cross v is that u cross v. This is the absolute value of this number that u cross v had been multiplied by. In this absolute value, the bottom of the fraction is already positive, so I only have to worry about losing any potential negative signs up top. This is removing this ambiguity here. Magnitudes of vectors are positive or zero, so I want the choice that's guaranteed to give me a non-negative result. On the bottom of the fraction, I have two factors of the length of u cross v. I have one upstairs, so I can cancel one of them out. So finally, we found a formula for this perpendicular height. You cross product u and v, take the result, form the dot product with w, take the absolute value of that, divide by how long u cross v is, and that is this perpendicular distance. The reason we're looking at this again is we're wanting the volume of that parallelepiped. We said it was going to be the area of the base multiplied by the perpendicular height. We now have formulas for those two things. Canceling the common factor out, we find out that the volume is the absolute value of w dot u cross v. That quantity inside the absolute value is sometimes called the triple scalar product. Since this represents the volume of the parallelepiped, and since we could relabel the names of the vectors any way you feel like, You can write these vector names down in any order you want. The absolute value of the result has to be the same. So if it's convenient to relabel them one way versus another, that's perfectly okay to do. That is to say, all 6 of these quantities are going to give you the same answer. This completes the material that I wanted to talk about in the introductory cross product section. Coming up next, we'll apply these kind of ideas to finding equations for lines in 3-dimensional space and also planes in 3-dimensional space. Until then, I hope everyone's having a good day. I'll talk to you again soon.